In this lecture, we are going to continue resist processing, looking at the kinetics and how this baking process and development process are going to help us in achieving the three-dimensional structure that we are looking for. So just to recap, we have a photosensitive material that is sensitive to a particular wavelength, and when you expose this material to that particular wavelength, the solubility changes. Right. So initially the material, the photosensitive material could be insoluble, but when you illuminate it, it becomes soluble. So we control this illuminating region so that we can define the pattern. So you can either use a simple photoresist, or you can use a sophisticated chemically amplified resist, and this chemically amplified resist are much more efficient. So instead of one photon delinking one polymer chain, this chemically amplified resist can delink multiple chains. So this allows you to use a lower energy of illumination to achieve the same amount of delinking that you achieve with a high power exposure when you are using a regular standard resist. And the kinetics also is pretty important. The absorption, what kind of absorption that you're looking for, and how the sensitizers and the resins are going to contribute for this absorption is also very important. So when you are developing a resist, make sure that the right amount of combination is required in order to achieve a desired result. So in this particular lecture, we are going to look at the kinetics of photoresist. So as I mentioned, we are going to look at the kinetics, and particularly when you expose the material, we know what is going to happen. But the next step, right, once you expose, we have to also bake this material. In particular, deep UV type resist, you have to bake the material in order to keep the reaction going on, or accelerate the reaction, or in some case arrest the reaction. So in both the cases you need to apply a thermal energy into this, right, what we call baking. So this baking can happen either before exposure, after exposure. So before exposure we call it as a soft bake, and after exposure we call it as a post exposure bake, and sometimes you also do hard bake, right, that is also after exposure. So all these bakes are doing two kind of process in the photoresist. One is soft bakes are trying to remove the solvent that we had, because initially we coat it and then we anneal or bake this material in order to make it solid. And the next thing is post exposure bake is used to accelerate the reaction, or arrest reaction as a result of exposure. And then hard bake. So hard bake again can be used, not always used, but in some cases it is used to again make the resist hard for subsequent etch processes, right. But these two are the first two processes, the soft bake and post exposure bakes are typically used. The hard bakes are used in special cases where you want to have highly resistant photoresist for dry etching, right. So the baking has a lot of important features. One is the temperature, the duration of bake, whether it is done before exposure or after exposure, and this is done in what atmosphere, right. When I say atmosphere, whether this is done in inert atmosphere or whether this is done in an atmosphere with water vapor, right. So all of this is very important in order to understand what goes on, right. And we will take a typical example of deep UV and understand how these processes develop, right. So annealing, first thing is about the temperature, right. What is the condition one should use? So there are two type of photoresist. One is a low density photoresist, the other one is a high density photoresist. So in a low density photoresist, we have large free volumes, right. So that means the material is loose, right. So there is large free volume. With a high density material, it's compact, very small free volume, right? So when you have large free volume, your acid, right, can diffuse quite easily. But in low or high density material, the diffusion of acids is pretty low. So what is the origin of this acid? So this origin of this acid is from photoillumination, right? When you illuminate this photoresist, there is a photosensitizer that generates this photoacid, right? So that is what this acid is all about. So this diffusion is different in these two materials, and as a result, we need to choose the temperature, right? So for type 1 resist, which is a low density resist, you want the baking temperature to be less than your glass transition temperature, Tg, while for a type 2 photoresist, you want this temperature to be greater than your Tg, right? So this is typically used as a rule of thumb, so that you choose the right temperature for baking, right? So when you are working with this low density or high density, make sure to understand the right temperature to choose, right? So look at the data sheet and choose the right temperature. And the effect of baking temperature and on this, or the baking itself, on the sensitizer, because this is the photosensitive material, right? So this material could decompose, right? So you want the sensitizer to remain sensitive to this particular photon, right? So when you do the soft baking before exposure at a very high temperature, then you might end up decomposing the sensitizer itself. So when you go for exposure, you may not see any photosensitivity at all, because you have killed the photosensitivity. So the temperature in which you do this baking is very important, and also the atmosphere. You don't want the atmosphere to react with this sensitizer and also decompose it, right? So you want to preserve the photosensitivity of your sensitizer. So make sure that you understand the chemical nature of this sensitizer, so that you use the right atmosphere and also right temperature, so that you don't decompose this material. And the next thing is about the solvent, right? So you will use this solvent after exposure, and also you will use the solvent that you have in the material itself, right? So how they diffuse and how they evaporate. So when you are using this solvent, when you are baking this photoresist, what can happen is, so this is your photoresist, you will have solvent going out of this material, right? And you need to make sure that your material hardens from bottom up, okay? So just to give you an idea, so when your temperature, right, is gradient, right? So this is your temperature. Your temperature normally, if you are heating from the bottom, your bottom temperature is higher, so the heat is from here. So your material starts hardening bottom up, right? So whatever solvent present on the top can escape. But on the other hand, if you are heating from the top, right, for instance, if you are using lamp type heaters, right, IR type heaters, it can heat from the top, right, or oven type heaters, it can heat from the top. So what happens is you will start to solidify the material on the top. So whatever solvent that you have, it will find it difficult to escape. So this will create some issues with solidifying your thickness, right? So make sure to understand the mechanism of your diffusion or your solvent evaporation, right? So this will create a local effect and a global effect on your thickness. And post exposure development is also important. So when you expose this particular part, and then now you're putting this material into your solvent, so the solvent is going to attack this part, but what happens to this material which is not exposed, right? There will be also some diffusion into this, right? So what kind of solvent one should use, and also what happens to this diffused solvent, right? Whether it is trying to remove this material or not. So one need to understand this diffusion very carefully. The way to understand is by looking at the photoresist sensitivity to the particular solvent, right? Whether the solvent will diffuse into this photoresist or not. So in order to understand that, read the photoresist data sheet, right? There is no generic rule that a particular solvent will dissolve or not. So they always go in pairs, right? So make sure that we understand this diffusion so that we can avoid this undesirable diffusion into the material. So after exposure, you are going to bake the material, right? Because that's what makes this chemical reaction accelerate. And here an example of a temperature is given, right? So after exposure, you bake at 110 degrees C through to 135 degrees C, right? Let's assume all of this is done for a minute, right? So when you increase the temperature, right, you can clearly see the pattern come out. So when you anneal at very low temperature, in this case 110 degrees C, the temperature is not enough to make the reaction, right, for wherever you have exposed. So in this case, you exposed in this part, okay? And you are trying to remove the material from the side. So as you increase the temperature, you can see that you are accelerating the reaction and you are able to achieve a good profile, right, at the end. So the photosensitivity, right, can be accelerated by increasing your temperature, right? And this also depends on the dose. So if you put more energy, right, you need less amount of heat in order to accelerate this reaction. So if I take this 32 millijoule, right, if you anneal at 110 degrees, your width is pretty low, small compared to a material that is annealed at a lower temperature, right? So you have to make sure that you use the right temperature so that you get the right dimension or line width here, right? So 105 gives you a broader one, right? But then if you anneal at a much higher temperature, in this case just 5 degrees change, 110, you will be able to get a better CD. So this tells us the importance of post-exposure bake for chemically amplified resist in particular. But this also applies for some of the unamplified resist, where post-exposure bake is important to get the right CD, particularly electron beam lithography. So the next property of resist is this contrast, right? How much energy is required in order to expose the material. So this is the contrast curve. So this is the exposed energy as opposed to remaining thickness. So here we take a blanket photoresist. So this is PR and this is your substrate. And there is a blanket illumination. So after illuminating with certain energy E, we are going to measure the thickness of this material, remaining thickness. As you can see here, the material doesn't show any thickness change for all these exposure dose. That means the energy is not enough to create all this photochemical reaction. And then you see a threshold, beyond a threshold energy, you see material starts to react, and then you are able to remove all the material, right? And this, the ratio of the E1, where it starts to react to completely removal of that material, is what we call contrast curve, right? So this is the contrast that we talk about, and it is important to also see this simulation that we have done. So a lower energy dose, going from left to right is energy difference. At the left end you see lower energy, and as you increase the energy you can see the material is getting exposed, and then completely we can remove this material, right? So this is a very important property of the material. So when you are choosing the photoresist, you make sure that this slope is very steep, right? So ideally you want it to be a box like curve, right? But in real world it is very hard to get, so you see that the slope is as steep as possible, so that a small change in the exposure dose will give you a complete removal of photoresist. And once you expose it, next thing is the development, right? So now we are going to put this exposed material into a solvent, right? And this solvent is going to etch this or dissolve this exposed part or unexposed part. In this case again we have an opaque part and then the transparent part here, and the colors here tell us as a function of time how the material, the solvent diffuses and makes the right profile, right? So when you are just 15 seconds, then you see the profile has a very large foot, right? But then if you increase the development time, then you are trying to make the profile much more steeper, but also you will see, you will also consume some thickness. There is always some baseline diffusion and erosion, what we call resist erosion from this development. So one should be also careful about how long can you put, right? So after this 30,000 seconds, right, and in this case even 1,000 seconds, you will not see any difference in the profile itself. So one should identify the right time, right amount of exposure time, development time here, so that you don't suffer from resist erosion. And the developers are of two class. One is metal ion contaminated and ion free. So why metal ion free and metal ion contaminated? This has a direct influence on the quality of silicon that we get, right? This is primarily applicable for people who are interested in silicon processing, because these metal ions can diffuse into silicon, and also they can sit on the surface of silicon, very hard to remove. And what they will do is they will change the conductivity. They will act as a strap sites, and then they will create issues with the electrical properties of this device, right? So that is where you have to use metal ion free, right? Tetramethyl ammonium hydroxide is another developer that one can use, and this is metal ion free, so you will not have any metal ion contamination, right? So you'll have a best quality electronic device, but the issue is these guys are pretty expensive, while the other one is much cheaper. So if you are not really caring about the electrical properties of the material or the substrate that you are using, it's better to use a metal ion contaminated one. But if you are very concerned about the electrical quality, one should go for metal ion free process, okay? And this is something we saw earlier, right? It's a long chain of process, and it is very important that all these processes happen without any delays, right? So the delay can cause some undesirable effects, and that should be addressed, right? So one way to address that is doing all these processes in a coupled platform system, and before doing that we need to understand what these delays can cause, right? So if this is what you want at the end, you might end up with T-top, and you can end up with a foot, or you can get this trapezoidal type impairment to your device, right, or your structure. So this is all because of contamination and the delays that you have in the system, right? one need to avoid this. So the way to avoid this is by using an integrated system, right? So all these processes should happen automatically, right, or in a quick fashion. In a R&D facility in your lab, you may not be able to have this expensive systems. So you make sure that the subsequent processes are done very quickly without any delay. And in industry, people use this track system, where the lithography tool is sitting here, but this wafer and the resist processing is a separate unit, right? All these processes are controlled, right? Like your coating, development, baking, everything happens within the system, and this happens in a controlled environment as well. So you control the humidity, you control your atmosphere, you control the pressure, so that your process yield is very high. In case if you cannot afford this kind of integrated system, still make sure that your subsequent litho processes happen without any delay or least delay, and also in a controlled environment. Make sure your temperature and humidity in your lithography bay is maintained. So in a resist design, right, one should make sure that all these properties are well understood. What is the sensitivity of this photoresist to the illuminating wavelength, the viscosity of the photoresist, adhesion of this photoresist to the substrate, what is the resist contrast, what is the resolution of this photoresist to the illumination that we have, thermal stability, because we heat and cool this material, right? So what is the thermal stability, and the etch resistance is also very important, because we are going to use this material for subsequent etch process, right? Make sure that we understand that. Purity is again very important. You don't want the material to be contaminated with ions or undesirable chemicals that will affect your subsequent process and your substrate. Charging is again very important. In optical lithography, this is not a big deal, but in electron beam lithography, it is important that you take care of charging. So we will discuss about this charging in electron beam lithography, but charging is again an important property that one should consider while choosing a resist. And then substrate compatibility, whether I can use this resist for all the substrate, right? So the substrate can be silicon, the substrate can be silicon dioxide, or you are looking at indium phosphide or metal, for instance. So there are various substrates one might want to use, so make sure that this is compatible. And the other thing is process compatibility, right? This is very important, whether I can spin coat this material, and then whether I can use this material in my plasma chamber for subsequent processing and so on, which is important property to understand. So when you are choosing a resist, make sure we understand this, or if you are developing a photoresist, make sure that you understand this requirements, right? This is again something we saw, so make sure that all these processes are nicely followed. And the coating the photoresist is an important property, right? So when you take a photoresist and you want to dispense onto the substrate, the way that we do is by using spin coating, right? We have looked at other chemical processes and physical processes. Spin coating is another process of material transfer, right? So there are 4 steps that we use in the spin coating. The first step is dispensing the material. So I take a substrate. The first step is dispensing the material. This is a fluid, so I just drop cast this material on top of the substrate. And the next thing is I'm going to spin. This is spin up, right? So in the spin up, this material is going to spread onto this substrate, right, covering the substrate. And the next thing is spin off, right? So what is spin off? So I'm going to spin this material and then make a very uniform thickness, right? And then you will always have excess material, right? So I want to remove this excess material, right? And then when you accelerate this, you will remove this material, what is called spin off. And the other thing is recoil removal. So whatever material that I have as edge bead, so I want to remove this. So this is called recoil removal. So all these steps are achieved by using the spin speed and time that we saw here. The first thing is spreading. This is what we call the dispense or the spin up step, these two steps together, right? It's the spreading step, and once you spread it, you want to achieve the right thickness that you want, right? The right thickness of photoresist. That is what the thinning is going to do. And finally, once the thinning is done, the recoil removal can happen at the end or after this as well. And then you reduce the speed, and then you take the wafer out of your spin coater. So the final thickness depends on multiple factors. One of the factor is your viscosity, right? So for any given viscosity, you achieve a certain thickness at a given speed, right? So your final thickness depends on your spin speed, right, for a given thickness, and this n depends on the solvent evaporation, right? So the solvent evaporation factor, either the solvent has no evaporation, right, during spinning, or it can have constant evaporation, or it can have variable evaporation. So based on the type of solvent evaporation mechanism, your final thickness varies, right? And this is all the constants which are empirically determined, right? And find out what kind of evaporation that you are having, and based on that you can achieve the thickness that you are looking for. So if this is the spin speed, right, and this is the thickness, normally for a given viscosity, your spin speed will reduce the thickness and give you the thinnest one, and then after that you will not see any difference in the thickness. So, and this is the low viscous one. If you have high viscous, you will always end up with a thicker film, right? So this is low viscosity, and this is high viscosity. So you can take any viscosity and you can thin it down to achieve a desirable thickness that you are looking for. So here there is a microscope image of a pattern defined on a substrate. On the left side you see the patterns are all grouped up. They are not in space or all jumbled on top of each other, but on the right side you see a very nice pattern. Wherever you want the feature is sitting there, right? Some of you who must have done fabrication can quickly recognize that here the patterns are nicely fixed onto the substrate or the coating that we have given, but here they are all floated, right? You have nice features though, right? So you have a very nice features defined, and here the lines are also very nicely done, but they are all washed away, right? So this is a problem of adhesion, right? So this is not just the patterning. Adhesion is also very important when you are handling optical lithography in general. So if you are going to address this lithography, one need to understand the surface chemistry, right? So when you take a silicon wafer, normally you clean the wafer, and so you will always have OH terminated substrate, right? When you come in with a resist, you might have a hydrophobic surface, right? And you want to make sure that whether the substrate is hydrophobic or hydrophilic in order to get the right adhesion. So in order to achieve a good adhesion, there is adhesion promoters are required, right? This is something that we also saw in this whole lithography process steps. Adhesion promoters are very essential in order to stick your resist onto the substrate, and also make sure after patterning these structures stay on the wafer, right? So these adhesion promoters chemically modify the substrate, right? And once you chemically modify the substrate, it creates a hydrophobic surface which has very good adhesion to the polymers that we are using. And normally your OH terminated substrates are hydrophilic, right? So you want to make sure that you create the hydrophobic surface when you coat it with the adhesion promoter, so that you have strong adhesion. So this always comes in pairs, right? Whatever resist you use, the adhesion promoter should be a complement of that. So they always go in pair. So make sure when you are choosing a certain photoresist, you also choose the right adhesion promoter, right? And you have this prescription from photoresist vendor, and also you can look it up in the data sheet of the photoresist what kind of adhesion promoter one can use. And there are some generic adhesion promoter, like HMDS is again a very commonly used adhesion promoter. It creates this polymer chain that promotes adhesion between the substrate and your polymer that you use as photoresist. So once you have the adhesion promoter in, and then you can be assured that the resist will stick onto the wafer nicely, and also make sure your patterns are nicely aligned as well. To summarize what we just saw, we saw photoresist kinetics, how photoresist evolve when you heat them up, and then how your reaction affects your profile, your development affects your profile, and also what is the effect of a photoresist on your development process, and what is the effect of adhesion on your photoresist process. So on a whole, it is not just choosing the right photoresist, and also choosing the right combination of wavelength and photoresist. It is also important to understand the photoresist process. What is the temperature one should use? What is the developer one should use? What is the baking temperature one should use? And what is the adhesion promoter one should use? So this is all important, and one need to be aware of these processes in order to achieve a very good litho process.